Okay, so let's start today's discussion, right. So we saw earlier that before 1950s you had mercury arc walls, right. 1950s you got BJT, but BJT of not much use for power electronics, right. Then you got thyristors again in 1950s, which became quite popular for high voltage DC transmission. So essentially they replaced the mercury arc walls which were being used quite popularly, right, because these guys were much smaller, much compact, more reliable, easier to transport. So thyristors became more popular. This is since again 1950s, and we saw the characteristics of the thyristors. So thyristors can be turned on by gate control. They cannot be turned off by gate control. The turn off happens naturally when the current flowing through anode to cathode becomes equal to or close to 0. Unlike a BJT, which you all know, right, BJT you can turn on, you can turn off based on the gate command. Thyristors cannot do that, they can only turn on, and therefore they are called as semi controlled devices also. Then came the MOSFET. So the MOSFET itself was invented again at Bell Labs around 1955 to 1960s. But then the high power MOSFET or the power MOSFET, right, which has a different structure, which has a different silicon structure as compared to the signal MOSFET, and that structure we typically call it as a vertical power MOSFET, was first introduced by Hitachi in 1969, right, so about 1970. So you understand that now 20 years from 50 to 70 you had thyristors, you could do few things, but you didn't have full control. As soon as you got power MOSFET, right, you got full control, because MOSFETs, as you understand, you can turn off, on, turn off using gate signal, right. So you got a bigger flexibility of building new circuits now. So this happened in 1970s. Now MOSFETs were good. So the left side is a picture which shows you one of the MOSFET. Again, what does this picture mean? The chip is inside this, right? Chip is inside this. The external one is just a package, right? So the pictures you see, it actually is a package, is an enclosure, right? The chip is somewhere inside it. You can package it in different packages. So in this picture, right side, you see there are these different types of packages, and there are many more actually in which you can have MOSFETs available to you, right? So although yes, this image on the left does sort of represent a MOSFET, but that is not a exact mapping, right? You can have MOSFET in any other packages also. So once you had MOSFET, a lot of things were possible. This is the structure, this is how the MOSFET looks like, right? This is how you draw it. There's a drain, there's a source, there's a gate to source voltage, and then there is something called as a body diode, right? What does a body diode means? Body diode means whenever there is a MOSFET structure like this, right, drain, source, gate. If you remember thyristor, for example, right, if gate is off, right, and you apply a positive voltage at anode with respect to the cathode. So imagine this as anode, this as cathode. If you apply positive voltage at anode with respect to cathode, it would not conduct if the gate is off, right. If you apply positive voltage at cathode with respect to anode, it would anyways not conduct in case of thyristors. But in MOSFET, the internal structure is such that whenever you apply a positive source, right, and negative drain, then the current starts flowing through this diode which always exists. So there are two main differences between this and thyristor characteristics. One is that, okay, gate can be used to turn off also, which is fine. The second is, if you apply negative voltage, right, if you apply negative bias on drain to source, which are the power terminals basically, the current will flow irrespective of the gate signal, because that diode is always present, and this is the structure in which it is connected, right. We call it anti-parallel diode. It's just a way of calling it. It's in a way it's a parallel diode to the MOSFET, but we are calling it anti-parallel because it's connected in a reverse fashion, right. This diode we are not externally connecting, it's inherent in the MOSFET, power MOSFET structure itself, it's inherent in the vertical power MOSFET structure itself, right. So that makes it a little bit different from an perfect ideal switch, right. If you had an ideal switch, you would expect that, when the gate is off, you apply positive voltage, negative voltage to the drain to source, nothing will happen. But no, in this case, if you apply source to drain as positive, the diode will conduct. If I want to draw the ideal characteristics now, let's say this is voltage between drain to source and this is current flowing from drain to source. When the gate is off, right, when the gate to source voltage is 0, let's say, right, VGS is 0, and if I apply a positive voltage across drain to source, if I apply a positive voltage across drain to source, let's say at point A, what will be the current that will flow from drain to source? What will be the current that will flow from drain to source? If I apply 0 gate voltage, that means MOSFET is off, right? It's an N channel MOSFET, 0 volt, MOSFET is off. If I apply drain to source positive voltage, what will be the current flowing through drain to source? 0. So, you will be at point A, right? In other words, if VGS is 0, this line sort of represents the characteristics of the MOSFET for a positive applied voltage, right? Irrespective of the voltage you apply, the current will be 0. Okay, what if I apply negative voltage? What if I apply minus 30 volt? What will happen? What if I apply minus 30 volt? Okay, let's start from that side corner. What will happen? What if I apply negative voltage between drain to source? That means now the source is at a positive terminal, drain it as a negative terminal. So, what will happen? What will be the current? Will it be 0? Will it be non-zero? Will it be positive? Will it be negative? This is my reference direction for I drain to source, right? So, will it be positive, negative or 0? Non-zero, but can you say positive or negative with respect to the reference direction I have shown? Yeah, so will it be positive or negative with respect to the reference direction which I have shown? I have shown a reference direction, right? This is my reference direction. Oh, no, you were right just before that, right? Current will go up. My reference direction is pointing down, right? I hope you are seeing the same thing which I see. My reference direction is pointing down. Sorry if you let me make it even more thicker. This is my reference direction. Right, it's going down. No? My reference current is going down. That means if actual current is going up, the current value will be negative, right? So that means I can never actually operate it at minus 30 volt because current would be just too much. So in the negative, if I try to apply even little bit of negative voltage, it will lead to a negative current. Okay, wait. We'll come to that. If I apply slightly negative voltage also, right, gate drain to source, even though gate is 0, the current will flow through this diode which I have drawn, right, and you will have a negative current. And this is happening even if VGS is equal to 0, right. How this current is flowing? It's flowing through the diode which I have shown, the anti-parallel diode, which is not an external diode, which is included in the MOSFET device structure itself. And therefore, it is also known as a body diode. Body diode means it's there in the body of the MOSFET, something like that, right? So, it's physically, it's there, we are not adding any external diode. Okay, now go ahead, what was your question? VGS is 0, yeah. That's why I am saying you can, so the structure of vertical MOSFET is different from structure of a signal MOSFET. You have learned signal MOSFETs? In some course you have read signal MOSFETs, right? Or MOSFETs. Which course you have read this? Analog, okay. What structure you would have seen is a horizontal structure, right? Power MOSFETs is a vertical structure. You can go back and try reading it once. Right, we can discuss it again. I don't want to include it as a part of this course, reading about the structure, so we are not doing it now. But you go back and you can see that in vertical MOSFET, you cannot just interchange the roles of drains and source, the way you do it in a lateral device. Hmm? Yeah. It may help, we will see. Sometimes it helps, sometimes it doesn't help. Yeah. But is the off characteristics fine? Any doubt, any more doubts in the off characteristics? Yeah, if you apply minus 30 volt, how much will be the current? Minus infinite, right? Because diode 0.7 it will turn on. If you apply minus 30, there will be like infinite current, right? So ideally, this will sort of exceed our screen size, and it would actually meet current somewhere like really large. Right? So in reality, you would not be actually be able to apply minus 30 volt. As soon as you apply even minus 1, 2, 3 volt, you will have a large negative current. Okay, let's come to what happens if gate to source voltage is now positive. Okay, now if gate to source voltage is positive, in that case, the drain to source becomes almost like a short circuit in ideal condition, right? So the device is on. So that means even if you apply slightest amount of positive voltage, you will get a positive current if the gate to source voltage is greater than the threshold voltage, right? And even if you apply slightly negative voltage, now you have two ways of current to flow. One is, of course, it can flow through that body diode, or now it can flow through the channel also, right? So the negative side sort of remains the same. So the off is represented by blue, the on is represented by green. And these are, of course, ideal characteristics. The real characteristics looks a bit more messy. Since you guys have already read about normal signal MOSFETs, let me just show you the actual characteristics also, and I think you are more or less familiar with it. We will not sort of go and try to understand it. If you recall it, that's fine. If you remember it, that's okay. If you don't remember it, don't worry. In this course, this would not be of much use. What would be of use is the ideal characteristics, right? So you have to remember the ideal characteristics for sure. Yeah, that's okay. That's okay. You can write 0, you can write less than V threshold. The positive one you can write greater than V threshold, or you can say, let's say 15 volt. Yeah. Because in reality, if you are just above threshold, you will not get a perfect vertical line, but these are ideal characteristics. So we can think of threshold as a sort of a clear demarcation between on and off. Yeah. Why is power MOSFET constructed this way is to make sure that they can handle much higher voltages. Therefore, the structure is required to be a little bit different from the conventional lateral MOSFETs. Yeah. No. So diode is sort of a byproduct which we get. Diode is not the reason why we are doing vertical MOSFETs. We are doing vertical MOSFETs so as to get a higher blocking voltage in the forward direction. Of course, diode comes as a byproduct of it, and which does help us sometimes. We will see later on in some circuits, it does help us, sometimes it doesn't help us. But diode is not the reason we did vertical MOSFETs, right? We did vertical MOSFETs because it gives us higher blocking voltages. So we can get a power MOSFET, so to say. Any doubt? Any more doubt? Okay. Then comes another guy called IGBT. Right? Now, what is IGBT? Essentially, there were power MOSFETs, but their voltages were still limited. Right? They were power MOSFETs of 100 volt, 200 volt, 400 volt, 600 volt, but then not beyond 600 volt, because again of the semiconductor structure, right? Semiconductor structure, semiconductor silicon properties, there were silicon MOSFETs, silicon power MOSFETs were not available for beyond 100 volt. And then so that happens in late 60s, and then in 70s to 80s, this is as per Wikipedia, B. Jayant Balika et al. Reported in 1982, the practical device capable of operating over an extended current range, which is an IGBT, is the first experimental demonstration of a practical discrete vertical IGBT device. in 1982, and subsequently it got, so this was done at GE, and then subsequently it got commercialized by GE and became widely available in 1990s. Now, what is this IGBT device? The full form is of course insulated gate bipolar transistor, but for power electronics engineer, what it means is that you get a device which can block more voltage than a MOSFET basically, right. So, if you say MOSFET was little power electronics, this could do more or rather higher power electronics, right, because it could block much higher voltage, it could allow much higher current to flow through it, right. So, this was essentially, imagine it as a more power oriented device than the silicon MOSFET, right. So, if you are talking about mobile chargers, right, you have to handle some 325 volt, 400 volt, few amperes of current, fine, one would use MOSFETs, right. If you are talking about some industrial drive, let us say you are talking about little higher power, maybe 1200 volt applications, one would go with IGBTs, right. Subsequently, there was another, two more names which became quite popular, IGCT and GTOs, right. Again, they were variations of the basic devices which allowed us to do even more voltages, even more current, so to say. So, if you look at the range, right, starting from MOSFET can handle the lowest amount of blocking voltages among these four of them, followed by IGBT, followed by IGCT, followed by GTOs, right. This was typically the increasing order of voltage handling among these four devices. Other than that, the four devices were more or less similar if you talk about their ideal characteristics, right. They were, all four of them were fully controlled, you can turn them on, you can turn them off, right. So, other than that they were similar. So, like for example, you can make a buck converter using MOSFET, you can make a buck converter using IGCT, right. If you want to make a buck converter which can operate at a 1700 volt, make it using IGCT. If you want to make a buck converter which operates at 100 volt, make it using MOSFET, right. So, essentially ideal characteristics are more or less same. Practically they are capable of handling different levels of voltages and current, and therefore they are, different devices, different structure. The other differentiation among them is the speed at which they can turn on and off, right. We saw an example that you cannot or practically will not make sense to build a buck converter using a mechanical switch. Why? Because the mechanical switch will not be able to switch very fast, right. Let us say you switch it once per second or something. Now, if you want to do a low pass filter, right, you have to cut off a very low order frequency. That means your filter has to be really, really big in size. You recall this example, right? You recall this example we looked upon in the first lecture probably. So, there is this circuit which is, there are two switches S1 and S2 and they are turning on and off very fast, right. And this would produce a voltage which is of this nature, right. And now you need a low pass filter which should allow the low DC component to pass through, but cut off any high frequency component, right, or provide a negative gain to the high frequency component. So, if you pass this signal through this low pass filter, if the frequency of the signal is, let us say F1, you would like the F1 to be somewhere here, right, so that you do not allow that F1 to pass through and you only allow the DC component to pass through. This is the gain, right. You have seen these kind of plots, right, gain versus frequency plots. So, this is a low pass filter, right, second order low pass filter. It's designed to stop F1 to flow through it and it's designed to allow DC with the unity gain to flow through it. So that after this you get almost nice DC voltage. Okay, is this fine? So far is it okay? Any doubt? Okay. Now you imagine this F1, what impact will it have on the filter? If your F1 is very low, let us say we are switching at 1 second, right, 1 second on, 1 second off, So your F1 is, or rather let us say time period is 1 second, so F1 is 1 hertz, right, versus if you are switching using a semiconductor device at a frequency of let us say 10 kilohertz. So 1 hertz versus 10 kilohertz, right. In 1 hertz your F1 component will be somewhere here and your 10 kilohertz is let us say somewhere here, okay. And now if I tell you which frequency would you prefer for this kind of a converter operation, which one would you choose, 1 hertz or 10 kilohertz? 1 hertz or 10 kilohertz? 10. Okay, how many of you said 10? Raise your hand. Very good. Anyone with 1 hertz? Okay, familiar face, please go ahead. Can you answer why? Why should we choose 1 hertz? Why should we not choose 1 hertz? Yeah, go ahead. Yeah. Okay, I will repeat the question. You have two options. You can use 10 kilohertz of switching frequency versus you can use 1 kilohertz of switching, 1 hertz of switching frequency. Which one would you choose for this application where you want to extract the DC component and you want to suppress this high frequency component to appear in the output? You have two options, 10 kilohertz versus 1 hertz. Okay, meanwhile as you think, next person. No answer, next one. Okay, that's a good answer. Further, anyone wants to refine it? Next person. Next one. Next one. But do you want to refine the reasoning? Answer is correct, reasoning is also correct, but do you like just want to add little different perspective to why one should choose 10 kilohertz? Next one. Next one. Anybody want to answer? Go ahead. Okay, all of you got what he said? All of you understood what he said? Okay, let's go back to our regular flow then. Yeah, go ahead. So, are you convinced with this argument? Not convinced. Okay, next person. Yeah, okay. Okay, that makes sense. So, what he is saying is that look, if you have a fixed low pass filter like this one which I have drawn, if you choose a higher frequency, right, you get more and more attenuation. So, in a way the output voltage be quote unquote even further refined DC voltage, right. So, if you use 10 kilohertz, it is better. If you use 100 kilohertz, it's maybe even better. You know, you would have negligible high frequency passing through that filter. It will be mostly DC. So, for example, you know, of course, it will have some small ripple at the output, right, along with the DC value. That ripple will become smaller and smaller and smaller if you keep using larger and larger frequency. So it would make sense to use larger frequency in general. The other way to look at it is, if my output requirements are the same, right. For example, I want to charge my phone battery and I say that my ripple should be less than 5%. So, if I fix my output requirement and if I am switching at 1 hertz, I need to make sure that I design a filter with a cutoff frequency much lower than 1 hertz. So hypothetically I have to design a filter something like this, so that at 1 hertz also I get sufficiently large negative attenuation, right. And to do that, what is the cutoff frequency? Omega is 1 by root LC, right. If my cutoff frequency is very low, then either the inductor has to be large or the capacitor has to be really large, or both of these guys have to be really large. So, if I have to work with lower switching frequencies, I will end up using very big inductors and capacitors, right. And therefore, in general in power electronics, you would see that we always want to use the semiconductor devices which can switch 100 hertz, 10, not 100 hertz, 10 kilohertz, 1 kilohertz, 100 kilohertz, even megahertz sometimes, so that we can reduce the size of these inductors and capacitor to get the same performance. So, higher frequency can lead to smaller LC, and this is the reason we would prefer to have a higher switching frequency. Okay. No, this is a large log scale basically, right? Generally plotted in log scale, right? Any other question? Okay. So, basic rule of power electronics is that you switch it really fast, create a square wave and then filter it out, try to minimize the filter size so that your charger can be small, your adapter can be small, your mobile phone can be small, and get a pure as close as possible to a pure DC output voltage. So now coming back to this picture, right, you see MOSFETs, the switching speeds are very high. As we move on to IGBTs, the switching speed reduces. As we move on to IGCTs, the switching speed further reduces, right. Therefore, if you have to work with voltages where MOSFETs can be used, you prefer to use MOSFETs. Yes, if you want to work with voltages where you cannot use a MOSFET, right, you would use something which is at a lower frequency, fine, you would have to use little bit higher inductor and capacitor, but still it would do the job. And all of these guys of course still switch much faster than the mechanical switch would do, right. So, we are still not talking about 1 hertz, we are still talking about relatively higher frequencies. For example, if I have to give you some practical value, let us say MOSFETs can easily switch at hundreds of kilohertz, IGBTs can easily switch at tens of kilohertz, IGBTs can switch at kilohertz. I am not very sure about GTOs, I think even further less, but this gives you a clear amount of idea of what we are talking about. Yeah, it's not coincidence. It's a bigger law, right? You know that law? Nothing comes for free. Yeah. So it's always this bigger law which comes into action, right? Of course, if you go in details, then you would see that their structure would not allow you to switch faster and so on, right? But that's how generally is, right? And since you asked this question, let me also give you one more input that cannot have everything concept, right? So there is yes, there is a trade-off between frequency and the voltage ratings, right? Let's say I choose a MOSFET which is at 400 volt. Now this MOSFET is capable of switching at, it can do maximum let's say 1 megahertz of switching, hypothetically. Now should I switch it at 1 megahertz or should I switch it at 100 kilohertz or should I switch it at 10 kilohertz? Let me repeat the question. I have an application, let's say mobile charger application. I picked a MOSFET which was suitable voltage rating, suitable current rating. Now this MOSFET can switch at 1 megahertz. It can, of course, if it can switch at 1 megahertz, it can also switch at 100 kilohertz, it can also switch at 10 kilohertz. Which one would I choose? 10 kilohertz, 100 kilohertz, 1 megahertz? Okay, how many of you say 1 megahertz? Raise your hand. अच्छे से उठाओ. 1, 2, 3. Okay, how many of you say 10 kilohertz? 8. How many of you say 100 kilohertz? Come on. Okay, what about rest of you? Why are you confused? Go ahead. Okay, use is the same. You want to, you have a battery of 5.5 volt and you want to generate 3 volt to charge your battery, let's say. So now what? No, forget about, I am saying right, you have a battery of, or you have a supply of 5.5 volt, you want to charge a 3 volt battery from there. Or would you do switching at 1 megahertz, 100 kilohertz, 10 kilohertz? 1 megahertz. Okay. Everybody else now? Does this number help you? How many of you think we should be switching at 1 megahertz? Raise your hand now. A little bit more. Okay, good. How many of you think we should be switching at 10 kilohertz now? Okay. You know why you are confused? Because you know that faster switching will help you in reduce the size of the filter, but you don't know what is the problem if you switch it faster, right? And therefore, in your mind, you only have like one condition, you don't have the other condition, but as per the law, nothing comes for free, right? So the other catch is that if you try to switch faster, you have more losses, right? We are not going into detail of that. You would learn it in some advanced power electronics course if you happen to do that later on. But if you switch MOSFETs, the same MOSFET, if you switch it faster, it can do 10 kilohertz, 100 kilohertz, 1 megahertz. If you do 1 megahertz, its losses will be almost, one component of the loss, which we call it as switching loss, become 10 times as compared to 100 kilohertz. So the losses increases if you are switching faster, and that's why there is always a trade-off. There is always a trade-off, and that's where the designer has to write the equation, try to optimize, try to figure out what is the optimal frequency, because if you take it too high, your LC becomes small, but the losses becomes more. If you take too low, your size system becomes bigger, the efficiency becomes very good. So you have to figure out the application, you have to figure out the device characteristics, you have to figure out where you want to operate, right? So it's always a trade-off. So given a device, so if you pick a MOSFET for example, right, there is always a trade-off between efficiency and size due to Fs, switching frequency. Okay, yeah. So now at least you can you got a sense of what we are dealing with, right? Otherwise you would have all be switching at very, very fast, very, very high frequencies. Any question on this slide? Very important slide. Gives you the whole crux of the logic behind power electronics. No question? Shall we move on? Okay. Yeah, so just to show you, right, so this is an IGBT with an anti-parallel diode, right, and I have shown you the ideal on state and off state characteristics, and you see this is ideal characteristics is same as that of MOSFET, right. So I already told you that MOSFET, IGBTs, IGCTs, they have same ideal characteristics. Any question? Okay. So in summary, these are the three categories. Okay, just for completeness, right, let us also have a quick look at the diode. We never looked at the diode. And let's draw the ideal characteristics of a diode, right. So if I say this is the diode, right, and this is anode, this is cathode, this is I anode cathode, how would the ideal characteristics of a diode be? Of course, in this case there is no gate, so there is only one, there is no gate control here, but what would be the ideal characteristics of a diode? Should I draw horizontal line, vertical line, in which quadrant, horizontal, which quadrant, vertical line? If VAK is positive, the current will flow, so it would practically never be able to have positive value, but you will have a positive current. And if VAK is negative, then you will have no current. Is that okay? That's fine. This is the ideal characteristics of a diode, right? All of you already know it. The real ones would actually be something like this. I'm sure you have studied it, right? Is that okay? Any doubt? Alright, so we have now these three categories of devices. One is uncontrolled, so to say. When we say controlled, uncontrolled, we mean the gate controlled, right? So it's uncontrolled, that means the on and off of the device depends on the power circuit, which is connected to the power terminals of the device, right? You don't have any gate control. Example is diode. You have semi-controlled where you have partial control, so you can turn on but the turn off happens only because of the power circuit. The example is mercury arc weld or thyristors, SCRs. Then you have fully controlled devices such as MOSFETs, IGBTs, where you can use the gate to control both turning on as well as turning off of the device, right. And together, we build different circuits primarily using these three devices plus lots of inductor and lots of capacitor, right. So that's, whatever circuits you would see, the rest of this course or rest of the power electronics part of this course, you would see either one or more of these devices combined with some LC, right. Okay, just for your knowledge, right, out of syllabus, there is something new which is happening, which is called as a wide band gap semiconductor based power devices, which sort of started happening. I mean, of course, the research was going on, but predominantly we started seeing commercial devices after 2000s, right. So basically, in these devices, performance improves further, you can switch much higher frequencies, you get higher blocking voltages. The basic idea is that you replace silicon with some other semiconductor, right, and you still use the same structure as MOSFET or similar structure as MOSFET, and now you build some new devices using that, right. So essentially in this case, silicon gets replaced by gallium nitride and silicon carbide. These are the two popular technologies, and this is something which is happening now. So in reality, I think you might have heard of these mobile chargers, right. There are conventional mobile chargers or adapters, and then there are new one which is based on gallium nitride based power devices, which are much smaller, right. And why they are smaller is because this gallium nitride based power devices can switch much faster than what a silicon MOSFET could have done, and therefore they are even smaller, right. So the same basic principles get sort of extended. So this is happening now. In this course, we will not talk too much about these devices per se, but again, in some advanced course you can learn more about that. So this is something which is happening right now. Any question? How many of you heard about GAN based devices? Okay, can you raise your hand completely so that I get a better idea? 1, 2, 3, 4, 5, 6, 7, 8, 9. If I may ask, how do you know it? How do you know it? How do you know it? Okay, so good. Yeah, so others who don't know it, just go back, try to Google GAN based mobile charger, right. I mean, and you can see it's very small, much smaller. It will be either small or it will be able to give you much more power. It can charge much faster in the same form factor. One way or the other, it has very high power density, right, as compared to the silicon one. Okay, thank you so much. And we shall continue with something else now. Okay, now from now for another few lectures, we will sort of do a little bit more dive into buck converters, right. We will only try to understand buck converter, which is one of the simplest power electronic converter. How many of you know buck converter? Okay, everyone knows buck converter, so makes my job much easier then. Motivation already we saw in lecture 1, right, that you have this requirement of stepping the voltage, DC voltage down at multiple places. This structure we have drawn for phone application, mobile application, right. We saw that you need something to bring down to 5 volt first, then 5 to 3.3, then 3.3 to 1 volt, right. So buck converter is a ideal sort of candidate for these kind of DC to DC conversion, which is stepping down the voltages. And then yes, this is also something which we saw. You could have done this with a motor generator set if you can afford to carry it with your phone, or you could have done with a resistance divider if you could have afforded to carry so much of heat in your pocket, or you could have done it with linear regulators, still so much of heat in the pocket, but then you get little better voltage regulation. But the best is what we are going to see now, which is the switching or PWM based converters, right, which is what one of its example is a buck converter. Okay, so let's get started with drawing the buck converter. Okay, there is an input voltage, there is a switch 1, there is switch 2, there is an inductor, there is a capacitor, and then there is this output voltage, and then it goes and connects to a load which is, let us say, RL, the load resistance. This here is an what we call it is an, of course, an ideal diagram, because in reality whenever you make an inductor, you would have some resistance coming along with it because there are wires. Whenever you make a capacitor, there is going to be some leakage current and so on. But in this diagram, at this level, we are considering all the elements to be ideal, right. So, remember, we are dealing with ideal elements at this point of time. We are dealing with switches S1 and S2, which also we are considering to be ideal. Ideal means they don't do any loss, they just turn on whenever we want, they just turn off whenever we want, right. So exactly, because in reality, there would still be losses in the switches, there would still be, milliseconds or microseconds or nanoseconds of delay between you give a command, it actually turns on, lot of phenomena, right. But for now, we are just making life simple, everything is perfectly ideal in this picture. We saw this circuit, right, just a couple of minutes back. We saw this circuit couple of minutes back. Okay. We saw this circuit couple of minutes back. Next person, no, the person behind you. Can you explain how it operates? Just in 2 sentences, right? Not beyond 2 sentences. Okay. Okay. He is saying something which maybe you have learned in some other course, right? But can someone sort of answer that how this circuit operates from what we were discussing just few minutes back, right? Next person. What we were discussing just few minutes back. You have said nothing wrong. What you have said makes sense, but I just want you to give the definition, or just repeat what we did couple of minutes back, because this is the same circuit which we saw a few minutes back, right? The person in the front. Okay. Okay, yeah, perfect, right. So, it's the same circuit, right. This is your element which creates, let me call this voltage as Vi. So, when you switch S1, let us say you turn on S1 here and here and here, right, and you turn on S2 in a complementary fashion, here this gap and subsequent gap, then what will you see at Vi? Whenever switch S1 is on, Vi will be equal to V in, and whenever switch S2 is on, Vi will be equal to 0, and then again V in, and then again 0, and then again V in, and then again 0, right. This is how Vi would look like. It has a DC component, it also has switching frequency component or Fs component, right. If I define some sort of terminology here, so let us say this is the total period which is Ts, right, which is 1 upon switching frequency Fs, and if I define this one as T on, right. When I say T on, let me say, I am in a way trying to say T on of S1, and if I define this one period as T off, right, in that case I can see that now Vi is this on and off switching waveform, and the rest is a low pass filter. So, what I will get at V output is, if my filter is designed properly, of course, what I get at output is only the DC component coming from this waveform. Is that okay? So, what will be the DC component coming from this waveform? If I have to find the DC component in the square wave, then I can, if I have to find the average component of Vi, right? How can I find average? 1 upon Ts integral 0 to Ts into instantaneous Vi into dt, right? That is what you would do if I ask you to find an average component of any periodic waveform. So 1 upon Ts integral of Vi I can split into 2, 0 to T on, right? This is 0 instant, this is, let's say, T on instant, and in this period Vi is equal to capital V in into dt plus integral of T on to Ts, the total period Ts, right? And the total period Ts is nothing but equal to T on plus T off, and in this period voltage is 0 multiplied by dt, and if you solve this, what do you get? You get T on upon Ts into V in, right? If I just, I define T on by Ts as something called as capital D, then this becomes capital D into V in, right? Yeah, you call D as the duty cycle. So we define D as the turn on period upon the total period, and we call it as duty cycle. So if V in average is D times, if Vi average is D times V in, this would be same as the output voltage average, because my output voltage allows the DC to pass through, and you get this relationship between the input and the output voltages. Is that okay? And this is what you get in buck converter, right? So you can find it this way, or you can find it another way, which I think some of you may know, but anyways we will still derive it in the subsequent slides. You can look at it either whichever way it helps you to understand, but yeah, the basic operation sort of remains the same. Any question in this one? So now if I change the duty cycle, or if I change the turn on period, if I make this T on smaller and smaller, my output voltage will become smaller and smaller. So I can adjust it, I can sort of tune it perfectly, so that starting from 5 volt I get 3.3 volt. Yeah, if you have done controls course, you can even change it dynamically, right? You don't have to keep duty cycle fixed, you can change it dynamically. You can measure the output voltage, you can compare it with the value you want. If you think the value is less, you can increase the duty cycle. If you think the value is more, you can reduce the duty cycle. You can do all of those things, right? Okay. Any doubt in this slide? How do you generate this signal which goes to S1 and S2, right? In reality, how do you generate the signal which goes to S1 and S2? You typically do it using a comparator. Let us say you have a triangle waveform repeating at a period of Ts, right? And you have a signal called Ref, which is somewhere in between. So your reference is somewhere in between somewhere in between 1 and 0, right? And you put this reference signal and this triangular signal and put it in a comparator, alright. So whenever reference is more than triangular, you would get a output signal S1 as high, and whenever the reference is less than triangular, you would get S1 signal which is low. Alright. So, if I have to draw, or if I have to draw the signal S1, to very carefully draw so that I can show you in the same timeline how things happen. Let's only focus on one period Ts. Let's not, everything would just keep repeating after that. So, at t equal to 0, the x-axis is time axis. At t equal to 0, whether your at t equal to 0 plus, your S1 will be low or high. S1 would be low or high? High, right? At this instant, yeah, let's name it something. Let's name it A. After A, your S1 would be low, and then again it will become high. I am only drawing for one Ts. Now you can imagine this signal keeps repeating. Okay? So far so good. Now this S1 I can give it to the switch in the previous converter, right? How do I relate the reference signal with the duty cycle, which is nothing but, so this switch if you see is on in two sides, so this would be T on by 2, this side is also T on by 2, and duty cycle is defined as T on by Ts. So, what I want to do is, I want to relate duty cycle with this reference signal, okay. So, it's basic trigonometry, can you sort of solve for this, that how would the duty cycle relate to the reference? So, how would you solve it? So, you see the top is a carrier which goes from 0 to 1 at Ts, right. So, you have to find the time instant at which it hits the reference value. You get the problem? So, it goes from 0 to the peak value, and peak value hits at Ts by 2. You have to find the instant at which it goes and hit the reference value, and that instant is nothing but T on by 2. So, I can write 1, which is the peak value, hits at Ts by 2, which is nothing but the slope of the straight line, is equal to the reference value which it hits at T on by 2. Is that okay? Just equating the slope. Now, I can replace T on by Ts as duty cycle. So, let me take T on this side. What you get is duty cycle is nothing but equal to the reference. Okay? Any question? Yeah. How do you get a triangular wave? I am sure you would have done it in your basic electronics course. How do you generate a triangular wave? Function generator. Kaun bola? Yeah. That's right answer. There's nothing wrong. Sorry. Yeah. Yeah. You can build a small analog circuit. You can build a small timer circuit. You can generate use a 555 timer or something. You can get a square wave. You can integrate it. You can get a triangular wave. That's how people used to do long back. Now nobody does it that way. Now nobody does it that way. Now what you do is all of this comparison, this triangle generation, reference comparison, everything is happening in digital domain, right? So essentially a microcontroller is generating a triangle inside, is generating a reference signal inside, it's doing a comparison inside. So all of this is happening in a digital domain, so you can program your microcontroller to do all of those things. Yeah, if you have to do it implementation in the analog domain or in the actual analog circuits, then yes, you have to use a timer to produce a square wave, and you integrate it, you produce a carrier wave, a triangular wave, then you compare it with the reference. Reference you can generate using a pot, then as you change the pot, the reference will change. As the reference changes, the width changes, at the width changes your output voltage also changes, right? Yeah, if you can generate a square wave with a variable duty cycle, you can do that as well, nobody stops you. Okay. Any questions so far? Okay, then let's come back to the same buck converter circuit, and now we would analyze it not in this sort of new way where there's a square wave and there's a low pass filter. We would rather analyze it in a more conventional way in which you have already seen the analysis. Question is, why are we doing that? Isn't this way the better and simpler? Just got the answer very quickly, very intuitive. Why are we going and analyzing in a different way? Because basically it's about learning one more technique. Then if you in future if you see some circuits, you can choose which way it's easier to analyze, right? Nothing else. So it's not that one is more correct than the other one. It's just that you should know both the ways of doing it, so that in future if you see a new circuit, a more complicated circuit, you can analyze it the way you want. Vin, Vi, S1, S2, LCR. Okay, we'll start with drawing the inductor current waveforms, right? How it looks like. So inductor current is IL. If I draw first Vi as we have seen looks like this, right, where if this is 0, this is T on, this is Ts, and of course the cycle keeps on repeating. How would the inductor current waveform look like? Let's assume that inductor current had a non-zero initial value. So it was initially at this point, I have shown it with the dot. Now you have to tell me how it looks like going from that instant t equal to 0 till t on. Will it, first of all, okay, basic question, will it rise or will it fall? There is an initial value, let me call the initial value as IL0. So now, will the current fall or will the current rise? Okay, how many of you say current will rise? Very good. Why would it rise? Yes? Yeah. Oh, okay, any one of you, go ahead. Okay, because the voltage is positive across. Okay. Yeah, so now there are, of course, what she is saying is correct. So one way to look at it is, if your circuit is operational from quite some time, right, and we know it is a buck converter, so we know there is going to be an output voltage, and we know the output voltage would be less than the input voltage because it is a buck converter. Now, right, you might ask me how do I know, and I will try to explain you later how I know. But assuming that you know this and the circuit knows this, that I am a buck converter, and it's been operational from some time, so the output voltage is less than the input voltage, and the assumption here is that you have a large output capacitor, right. Now this is an assumption which we generally take in some of the circuits, and there is another name for it, we call it small ripple approximation, right, and these other names would tell you why we take this assumption, because the output of this, where will it go? It will go to the battery, maybe, it will go to your processor chip, and you cannot afford to have large ripple there, right. So your ripples would be like less than 1%, maybe less than 0.5%, right. So you can imagine the output capacitor voltage has to be really stiff, right, it will have very small ripple. How is that possible? Unless you put a big capacitor at the output, right. So the assumption of having a large output capacitor is same as the assumption of having a very small ripple at the output, and that is what we take for the time being, right. It's not mandatory to do that, but that sort of simplifies the basic operation understanding. So if I assume that my capacitor is large enough, that means I am assuming that the output voltage is almost constant. So in this region going from 0 to T on, I can assume that my output voltage is almost constant. If I draw the equivalent circuit of this, it would be V in, switch S1 is closed, right, S2 is anyways open, there is an inductor and there is a cap and R, but this whole thing I can assume it to be stiffly maintained at V0, and therefore I can write V in minus V0 is equal to L dIL by dt, right, and if I assume V in is more than V0, di by dt becomes positive, slope becomes positive and my current would rise. Is that okay? Any doubt? Any question? How will it rise? Will it rise linearly? Will it rise exponentially? Will it rise as if it's going to saturate at some point? How will it rise? Okay, one by one. How many of you think it will rise linearly? Raise your hand. Okay. How many of you think it will rise exponentially? Raise your hand. Come on, one person at least. How many of you think it would rise exponentially? Raise your hand. One person please. Ah, great. You have to answer it, huh? Acha. First I am looking for somebody with that exponential. Then I look for somebody with this exponential. First I am looking somebody with exponential. Anyone who thinks it will go exponential? No one? Okay, fine. Then the other exponential? Okay, go ahead. Why do you think so? Okay. So let's sort of say option A, option B, option C, right? Of course, option A, B, C does not lead to the same final value, so don't worry about too much. It's just the general shape I'm talking about. So option A, option B, option C. Is visible? Are these options visible at the back? Okay, good. So option A, yes, because if you see this equation, V in minus V0 divided by L and you integrate, right, V in minus V0 we have assumed it to be constant, so V in minus V0 is constant divided by L, if you assume it to be constant, it's constant, integrate it, you will get a straight line, right. So option A is definitely fine, there is no problem with that, with this being an ideal circuit, right. Option B and C can happen if this is not an ideal circuit, right. What do I mean by that? Let's say, okay, this is again out of syllabus, but let me tell you, because let's say there is a small resistance in series with the inductor. Yeah, there is small resistance in series with an inductor. Now what will happen? The differential equation will change slightly. You will have V in minus V0 is equal to L di by dt plus I into R, right? And now what is the if you solve this equation, right, you have already done Laplace and solving it and so on. If you solve it, what kind of response will you get? Will you get B or C? You will definitely not get A now, but will you get B or C? Will you get B or C? How many of you say C? Okay, don't worry, let's sort of do it this way. If I apply a voltage source, to an inductor and resistance, right, what will be the current waveform? First it will rise very fast and then it will slowly try to limit to some value. Okay, so slope would be fast in the beginning, slope will become lesser gradually because you have this IR drop coming into picture. So B or C? B? No? Confused? Okay, go ahead, anyone? Okay, how many of you think B? First let's just see how many of you understood it. Okay, then now what is the confusion? Go ahead, I'll repeat myself if there is anything. Any question? Okay, any question on B? Any doubt on B? Okay. So if you imagine there's a small resistance along with that inductor, that will not rise linearly, right? It will rise more like trend B, right? Like an RL circuit basically, right? RL circuit response. Okay, so B is possible if it's a real inductor. If it's an ideal inductor, B is not possible, right? So A is ideal. Of course, we have already taken this main assumption that the output inductor capacitor is Raj, right? So don't forget about this assumption. A is ideal, B is real if we consider R plus L. Can someone answer me if C is ever possible? Is C possible? Okay, yeah. He's saying if there's a capacitor, you might get a response like C. Is this possible? Any other answers? If VO is not constant, yes, you may get some strange waveform, which I feel might be more similar to B rather than C. So, any other answer? Can you get C ever? And this is where you have to recall what you learned in the previous course. This is where you have to recall what you learned in the previous course. We learned about inductors in the previous course. We learned about cores in the previous course, right? We learned about the core properties in the previous course. Do you remember it? We learned that if you apply a positive voltage to a core, right, its flux will rise, right? If you keep applying the positive voltage, what will happen to the flux? Okay. B is proportional to flux, E equal to N d phi by dt, right? So the more time you apply the positive voltage across inductor, right, your flux is growing up, correct? And as flux is going up and flux is going on linearly almost equal to N d phi by dt, so the more time you apply, the more flux becomes, but you are moving towards saturation. So for each increase in flux, the initial increase in current will be small, but then same increase in flux here would lead the increase in current to be very, very large, right? H is proportional to current. So therefore, initially, see some small slope, but then the slope will keep on rising. So you can have C if your core is a saturable core, right? You can have a C also, that's a possibility. Sure. So if you have if you have a voltage applied across a core, which is what you are doing here, right? You are applying a positive voltage across an inductor, which is a core with a winding. Then E equal to N d phi by dt. So voltage is positive. As time increases, your flux increases linearly. There is no question about it. But the relationship between flux and the current H is non-linear. So even though flux is increasing linearly, H is increasing much faster, right? So therefore you would have a trend like C. In reality, the C would look something like this. Let me draw it over and above. If you had an ideal characteristics A, then C would look like this, like peaky. It would start with the same inductance value, but eventually the inductance value is becoming smaller. So your size is becoming sharper and sharper, right? So this is actually the real C, how you would see it. For now, let's just stick with the A. Yeah, it's linear. What happens at T on? What happens at T on? Your switch S1 is open, your switch S2 is closed. The equivalent circuit in the rest of the period becomes something like this. If I write, it will become minus V naught is equal to L dIL by dt. Okay, and therefore the inductor current slope becomes negative, it starts falling and it comes back. Alright. So this is how the inductor current waveform looks like, and it keeps repeating as the switch is turning on and off and on and off and on and off. Now just one point I would like to make here, which I have seen a lot of students, not a mistake but lot of students do it that way. When you are writing the voltage equation for inductor, right, reference direction you keep it to be fixed. Don't change the reference direction going from switch on to switch off. What I mean is, if you see when switch on, I had the same reference polarity, left side positive, right side negative, VL, and I had the same reference direction current going from left to right. When I went to switch S2 on case, I still kept the same positive and the negative reference polarity and the same current direction polarity. Of course, the actual values might have changed, right? Now in this second case, we see the VL comes out to be negative, but the reference, don't change the reference, otherwise you will get confused, right? So fix the reference for a circuit and maintain the same reference throughout its operation. Don't change the reference as the switch is turning on or off or something like that, right? So that it just makes it very simple, and you get di by dt as negative, you can just draw it as negative waveform. Any question, any doubt so far? Okay, he is asking what does the initial current depend on? We will see in the next class, not today. Any other question? Of the inductor current? You can imagine, right? You can imagine. You can imagine if, for example, if it is saturating, it will go like this, then initially it will fall asleep because inductance is small, then it will fall. So it will be like this, right? You can do that. Okay, I'll see you next week then.